Hi, my name's Steve Urt. I'm part of the Havok team along with Petr Metrovich. I'm going to present some of his work on getting more stable physics for free. In other words, we want to create a stable stack of bodies without caching any extra simulation data. Let's break down what that means. A little bit of background first. Havok partnered with Unity to provide a physics solution for their data-oriented technology stack, DOTS. And the Unity physics solution that we provided should be data compatible with the Havok physics SDK. So both simulations could drive the data there. And it should be customizable and have source so that developers can learn and tweak the engine to their heart's content. And it should also be network friendly. For things like determinism and easy rollback from one simulation step to a previous time. So with stacked bodies, a lot of bodies stacked on top of each other, we're going to need to have a fast physics solver. And a fast solver is going to introduce error. But errors are going to accumulate and lead to an unstable stack. And normally, that error is recorded from one frame, and that information can be passed to the next frame in order to clean up those errors as you go from step to step. Without this error cache, small errors accumulate and the stack gradually drifts and collapses on its own. But with that cache, you're going to have to collapse the stack yourself. The error cache does make the code more complex, and it makes the network use case trickier. So how do we square this circle of not having a cache but wanting a stable stack? Let's break the simulation step down a little bit. So any simulation can be broken down into a series of steps, usually maybe about 60 every second, and it's going to involve collision detection, collision resolution, and then at the end of that, we're going to apply other forces like friction. For the collision detection step, we're going to get information like the shortest distance between the two bodies that are colliding, a separating plane and direction that the body should stay on the correct side of, and a contact point or a number of contact points that should be used in terms of positions on those bodies that we should be applying forces. For the collision resolution, we're really ultimately wanting to keep all of those contact points on the correct side of that separating plane. We're talking about contact constraints here. And friction that's going to be calculated at the end is another force that is going to use all of that information from the resolution of the contact points, the total number of the total impulses that we've applied to keep those bodies separate can go into calculating a friction impulse. So the implementation of choice for a physics engine, a real-time physics engine, is normally the Gauss-Seidel solver. It's an iterative solver, so we iterate over all of the contact points. And we get a rough approximation at the end of that iteration. To increase accuracy, we can have a number of these iterations over all of the contact points, but there are diminishing returns. So we normally cap the number of iterations to around 4. And deal with the error is small enough at that point. But we're still introducing small errors. We're introducing them from the fact that we're solving each constraint consecutively and the fact that we're capping the number of iterations. Now, the rest of the presentation, I'm going to be talking about contact constraints, but there might be other constraints involved in the simulation as well, like ball and socket and hinge joints, but we'll focus on contact constraints for this presentation. Okay, so looking a little bit more detail in the Gauss-Seidel solver, consider the box with 2 contact points. We're looking at individual contact points one at a time, and whenever we've calculated a solve for that particular contact point, we're overriding all of that information, like the velocity on the box, for example. And we're hoping then that the number of iterations that we include, in this case 4, converges towards 0 error, but the likelihood is we're going to have some error. So if we consider a box with those 2 contact points, we're going to solve contact point on the right first. It's actually going to introduce not only a linear component to keep the box off the ground, it's going to introduce an angular component because it's rotating the box at that contact point. However, on the next step, we're going to look or the next iteration of the contact points, we're going to look at the contact point on the left, and hopefully it's going to reverse that angular effect and apply a linear and an angular impulse to the box, which should converge towards 0, but it might end up having a residual angular component that we don't really want. So just at high level, we're looping over all the contact points, we're applying collision resolution forces, we're accumulating those collision resolution impulses in our case because we're changing velocities. And from that accumulation, we can apply a friction, as in the sort of sideways movement of the box, based on how much impulse we applied to the collision resolution upward impulses on the box. And hopefully with the number of iterations, as I said, we end up with a stable box that's not moving and there's no residual velocities. But perfect is the enemy of good enough when we want performance. So we're going to need some fix-ups. And the first fix-up we need to do is with friction. We're capping the number of iterations. We're introducing these issues. Let's look at friction first. So friction is actually quite a simple calculation, really. The idea here is to take a linear velocity and introduce some angular velocity to reduce the linear component and add an angular component. And the aim here is for the contact point between the sphere in this case and the plane that it's rolling along. The relative velocity at that contact point should be 0. We should go towards 0, assuming we have a friction value of 1. If it was ice, for example, we wouldn't introduce any friction. So here's the problem that we have with friction whenever we're dealing with this iterative solver scenario. In this multi-body situation, we've got a number of solve pairs. We're going to look at body 1 with body 2. Body 1 has got an initial velocity coming in from the left. It's going to hit body 2. And body 2 is then going to get a velocity from that impact. And the next thing we solve is between body 2 and body 3. And that is going to apply our contact resolution and our friction calculation, which is also going to introduce this angular effect from the friction. And then the final thing we solve between body 2 and body 4, because we do dynamic versus static bodies at the end. So all the yellow objects are dynamic bodies, the black object is a static body. And we want to prioritize static dynamic collisions over dynamic collisions. But in solving 2 and 3, we've introduced this angular velocity. It was correct at that point in the solve iteration, but it's wrong at the end of that particular simulation step. So although body 2 didn't move, we have introduced this angular movement on body 3, and then over time these small velocities could cause a drift in our stack. So these small these intermediate velocities can really affect the friction calculations quite significantly. Okay, so normally we solve this problem with extra state. We can cache that extra information, like how much friction we applied on a particular body pair, and we can pass that information to the next step. We don't want to do that. We don't want to remember what was on the previous step. We want to have a cache-free scenario so that we can just roll back our simulation very simply. But without that friction fix-up from that friction information on the previous frame, we're going to introduce that rolling on body 3, and that's going to accumulate over time and cause our stack to fall down. So one way of doing this, we want to aim to reduce that those problems with the friction calculation. So one way of doing that without introducing cache is to copy that initial velocity. Remember, the initial velocity of body B at the start of the step was correct. It was 0. It was 0 at the end of the step. We're going to copy all of those initial velocities at the start of the step, and then we can have some sort of choice between that initial velocity when we're doing a particular solve and that intermediate velocity. So at heuristic time, we need to have some sort of function to choose between those two velocities. And we can pick a simple heuristic. It might be just to minimize the energy in the system. We don't want to introduce more energy. That's what's causing our problems with the stack drifting. So the simple heuristic of minimizing energy could simply just choose the smaller velocity. So if we do that, then when it comes to solving between 2 and 3, our heuristic is such that we pick the lower velocity for body 2, which was 0 going into the step. That 0 is used to calculate the friction, which does not introduce any angular effects. And therefore, by the end of the step, after we've solved all contact pairs, we don't have any extra angular effect on body 3. So that was a fairly simple scenario, just for example. Spheres are easier to look at because there's only one contact point with the box. But if we consider our stack of boxes from the very beginning, there's a lot of contact points involved, and that central box in the middle is going to get a lot of angular effects from dealing with all of its neighbors. But it didn't have any initial velocity going into the step, and despite the fact that there's a lot of contacts going on with that particular box in the center, using this heuristic, friction won't introduce any more drift because we're choosing the lower of the velocities between initial velocity and intermediate velocity. Okay, so we've fixed friction, and we've seen that the angular elements that we're introducing from these errors is the real problem here. So we've got other issues to consider. We want to reduce those angular effects that are invalid from limiting the solver iterations. We don't end up converging. So we need to slow spinning. We need to stop that angular effect. So the solver is trying to converge to a correct result. It's giving us diminishing returns. The more iterations, the less movement we get towards 0 error. We could just cap those iterations and use some fancy fix-ups in order to get us to 0 error. Let's see if we can do that. At this point, I want to introduce an idea of effective mass. If we try and lift the heavy box and we lift it straight up through the center of gravity, that green dot, we're just applying a linear effect, a linear velocity change to that. So we're feeling all of that mass. Mass is to do with the linear element of a body. If we use a long lever to try and lift that box up, it doesn't feel as heavy, but we're introducing these sort of angular elements to it, and we're going to have a number of levers on either side in order to lift the body by the same height. But it's the mass we're feeling when we lift the box directly or lift it with a lever is what we call effective mass. It's the mass we feel. So when we consider issues with the stack bodies, we want all of those linear changes. We want the collision resolution to be lifting all of our boxes through the center of mass, and we don't want those angular side effects. But because the contact points are where they are, we of course are going to introduce those angular components anyway. This is completely aside from the friction element that we saw before. So we have to improve convergence by reducing those angular changes. When we're applying impulses at the collision resolution stage, we're applying an impulse at that contact point. So the angular element of that is going to be dependent on how far away that contact point is from the center of mass, and also the sort of direction of that impulse. The more in line with the arm, as it's called, the less angular effects that you have. The more tangential, the more perpendicular to that arm, the greater the angular impulse that you're going to introduce. So the impulse that we're applying, again, for collision resolution is going to be based on that effective mass idea, i.e. how far away we are from the center of gravity, and also the velocity change that's needed to take a moving body that's colliding with, say, a static body. We need to stop it. So there's a velocity change there. And the contact point is going to have an effective mass. It's going to have a mass that it feels at that particular point. Now, if we're moving a body through the center of mass, it's going to give us the same result as if we're moving, like say, boxes on a palanquin or a bench or something, and we had two people lifting each side of the bench. It's going to give us the same result as lifting the through its center of mass. We're not going to introduce any angular effects here. But really, with the iterative solver, we're really talking about two levers lifting the box. We're effectively lifting one side of the box, then the other side of the box. So we are going to have intermediate angular effects, but we want to reduce those angular effects. Okay, so how do we do that? We've got our contact point. We're going to apply a vertical impulse at that contact point to keep that contact point on the correct side of the separating plane. The easiest way to reduce the angular element is to increase the inertia of the rigid body. So the mass was affecting how difficult it is to move the body in a linear fashion, and the inertia is the equivalent of how difficult it is to move a body around its center of mass, to rotate that body. So we want to increase that. Okay, so I'm not going to go into the details of the calculations. It's just there for reference, but the effective point mass is going to be a product of the offset from the center of mass, the mass of the body itself, and the inertia of that body. Now, we tend to use the inverted mass and inverted inertia because it's just quicker to invert the mass and inertia once at setup, and then do a multiplication rather than a division through all parts of the code. It also is quite nice because we can actually zero out the inverted inertia, which gives us an infinite inertia, i.e. a kinematic body for free. Another free element. Okay, so the impulse that we're going to calculate for a particular contact point is going to be based on that relative velocity between the bodies and that point effective mass that we've calculated. So the actual velocity changes both in linear and angular components. You can see that they're going to be based on the impulse that we calculate, the mass of the body for the linear components, and the inertia of the body for the angular components. And we want to reduce that point effective mass by reducing the inverted inertia or increasing the inertia. Okay, so it's heuristic time again. So too much inertia or just arbitrarily increasing inertia for all bodies is going to introduce inconsistencies. We're going to get too stable stacks. We're going to get bodies that sort of fix at odd rotations. So we don't want this too stable behavior. So we need some heuristic that's going to apply an increase in the inertia with a little bit more finesse than just applying it to everything. So we've now got a new aim to help convergence on the solver by scaling up inertia. We don't want to arbitrarily scale inertia. So we're going to scale it based on the number of contact pairs. Consider that box in the center of the stack. It's got a lot of bodies that it's contacting with. If we can increase inertia and scale it based on the number of contact pairs, we should be onto a good thing. So this is just a simple example of the formula that's in our code base. We scale the inertia based on the number of contact pairs, but we don't do any scaling if there's only one contact pair. There's one body sitting on a flat plane, for example. But we can see here that if there's 2 or 3 contact pairs, we can increase inertia by a factor of 1.4. It's worth noting that that particular number of contact pairs is calculated per step. So we're not keeping information from a previous step. We're calculating that new heuristic every time. So if we look at our stacked body, body 1 in the center there is contacting 6 other bodies. So we end up effectively doubling its inertia, and therefore subsequently reducing all of those angular effects that come from the contact points being applied at the corners of the box. So as a result, the stack shouldn't fall apart. Now, we've fixed friction. We've helped convergence of the solver by slowing down spinning, increasing inertia, but we still have some residual errors. So we need to do something with those final errors. They hopefully are smaller than they would have been with friction being a problem and inertia being not scaled. So we want to trim the tempo on those final small residuals. So again, we are using an approximate solver. It's leading to small errors. If we have fast bodies, we don't care about those small errors. They're probably not going to be noticeable, but we've got stable bodies in a stack, and those small errors are going to build up. One simple solution is just to kill the small velocities and remove them. That'll drop the error to zero because the velocity will drop to zero. Okay, so we need to look at methods for killing those small velocities. We could damp, that is, reduce the velocity each frame by some factor. We have damping in the engine anyway, and it's not really helping us because it's not removing that error altogether. We could reduce the velocity by some fixed value, but that's pretty arbitrary. Or we could clip the velocity below a threshold. And now again, we're into heuristic time, because what is that threshold? So the threshold that we want to clip our velocities below, if the velocity is below a certain threshold, we want to put it to zero. It should correlate with the artifacts that we're seeing in our simulation. And small velocities are typically causing those problems. So we really want to clip those small velocities. But we also have to remember that what is small, a small velocity is going to feel different for a 1 centimeter object compared to a 1 meter object. It's the old, is this smaller, is this far away type problem. If our threshold is too high, we're overly aggressively clipping, and we're going to lead again to more overly stable scenarios. Stacks that shouldn't stay upright, stacks that don't slide down slopes, or in the worst case, a stack that floats because gravity is applying a tiny velocity to make things fall from a zero velocity. That tiny velocity is added to the body, but then we clip that tiny velocity in our threshold calculation. So we end up with a floating stack. That's obviously not a good idea. So we want to clip the threshold, but we don't want to put it too low. Otherwise, there's no point, and the user is going to see all of those accumulated velocity problems that we've been trying to avoid for the whole presentation. We've already helped the solver converge towards a smaller error with friction fix-up and inertia scaling. So we need to look at clipping that final tiny velocity. So these are just some example threshold heuristics. There's separate linear and angular values for our thresholds because they're slightly different problems. We are using per time step or per step information like time step and gravity because they could change over time. Also, the body size is included in the angular threshold because a bigger body should have a bigger inertia, and therefore our threshold should effectively be bigger as well. And we could include other factors here. We're not. We could include things like the number of contact pairs, as we did with the inertia scaling. But this was a simple scenario. So implementing that very simply, if the linear velocity of the body is lower than the linear threshold, we set it to zero. We could keep the gravity component, for example, and just trim off the movement left to right and leave the component that's being applied by gravity. That's an option. We could look at these thresholds, the linear and angular thresholds, separately, or we can only say apply angular clipping if the linear clipping happens. So there are a lot of options for this heuristic, and your own scenario is going to be the driver of which one you wanted to go with. Okay, so in conclusion, we've got a stable stack of bodies. We've fixed friction by using that input velocity rather than the intermediate velocity in certain scenarios. And we've helped the solver converge towards zero errors. We've slowed the spinning by scaling up the inertia based on the number of contact pairs. And we've trimmed off that final residual piece of velocity that means that we could get a little bit of drift. So with no extra state, we've got a stable stack of bodies, or indeed more interesting configurations like seesaws that balance out their masses in interesting ways. So hopefully that was useful information to you. Please go to the GitHub repo where all of the samples that you've been seeing here have been uploaded for you to play with. Find out more information about the partnership with Havok and Unity at the web address, and go into the simulation and turn on that heuristic just to see what the sort of stable stacking scenarios are going to be available to you. Thank you for joining me today, and enjoy the rest of your GameStack Live.